Mars looks calm from a distance, a small red sphere drifting through cold light, but every layer of its environment contradicts what human life requires. The air is thin to the point of absence. The soil holds toxic chemistry. The radiation is unfiltered and persistent. Water appears, then vanishes again, locked in ice or bound in minerals that never melt. By all measurable standards, Mars is not simply hostile, it is structurally incompatible with biology shaped by Earth. Yet we are planning to go. This contradiction carries weight. If a world cannot support us, what does it mean to choose it anyway? The implication is subtle. The boundary between habitable and uninhabitable is no longer fixed. It depends on our knowledge, our technology, and our willingness to define life beyond natural conditions. So we face a question that is both scientific and human. If Mars rejects life at every scale, why does it feel like the next place we should inhabit? The answer starts with a fact that seems almost quiet. Mars is uninhabitable because it lost something fundamental, a thick, protective atmosphere. Without pressure, warmth escapes. Without a magnetic shield, radiation enters. Without stable water, chemistry slows. These losses shaped the planet we see today. A world carved by time and thinned by space. To understand why we are moving there, we first need to understand what Mars became and why it remains scientifically irresistible despite all that it lacks. Mars is uninhabitable for a simple, measurable reason. The planet's atmosphere is so thin that standing on its surface feels like standing at an altitude far above Earth's highest peaks, where the air cannot sustain breathing, combustion, or liquid water. The pressure is so low that exposed water boils rather than melts. Even a shallow puddle would vanish in moments, lifted into vapor by physics alone. This calm fact sets the stage. Mars cannot keep the essentials of life on its surface. Yet when spacecraft orbit the planet, they see traces of rivers cut into ancient rock, valleys that once carried flowing water, and sediment layers that formed only where lakes once stood. Light moves gently across these shapes, revealing a contradiction, a world that was once wet and warm, now cold and still. We observe the remnants of a climate that could have hosted life, preserved in silence for billions of years. This contrast becomes a natural reflection. Earth is dynamic, thick with atmosphere and heat. Mars is the opposite, a planet that lost its stability and froze in place. When we look at Mars, we are seeing a paused story, a record of planetary change written into stone, rather than weather. Every few hundred words, a deeper visual helps. Dust moves across the Martian plains with surprising speed, lifted by winds that persist despite the thin air. The dust spreads over kilometers, softening sunlight until the sky becomes a muted red. Even this movement carries a lesson. Mars is active, but not alive. Everything shifts, but nothing grows. From here, scale becomes useful. Earth's atmosphere is nearly 100 times thicker. On Earth, breathing is unconscious. On Mars, the lack of air demands constant engineering. Every habitat must resist internal pressure trying to escape outward. Every suit must create a pocket of Earth-like conditions. Human lungs cannot adapt to near vacuum. There is no path for biological adjustment. Only technology bridges the gap. This leads to a micro-story, a small moment to ground the science. Imagine opening a hatch directly to the Martian air. Inside a habitat, pressure keeps everything stable. The moment the door unseals, the air rushes outward, not inward. Papers lift, fine dust pulls inside, and the moisture on any exposed surface evaporates instantly. A brief, sharp stillness follows. It is the silence of a world without breathable atmosphere. The reflection that follows is quiet. We evolved on a planet that holds us in place, with gravity, pressure, and warmth. Mars offers none of these by default. To live there means to recreate Earth in fragments, inside domes, suits, vehicles and tunnels. Each enclosure becomes an island of survival, surrounded by open, barren land. But even this is only part of the story. Temperature amplifies the challenge. Mars is cold not only because it is farther from the sun, but because its atmosphere cannot trap heat. Daylight warms the rocks, but the heat radiates away quickly after sundown. In many regions, nightly temperatures fall well below anything naturally experienced on Earth's surface. These cycles create stress in materials, expanding and contracting structures over time. Light shifts again here. Shadows grow long across dusty ridges. The land cools rapidly as the sun sets. In the thin air, there is nothing to hold the warmth. The surface radiates energy straight into space. Radiation adds another layer. Without a magnetic field strong enough to deflect solar particles, Mars is constantly exposed. The surface receives levels of radiation that exceed safe limits for unprotected humans. This is not a dramatic burst or sudden event. It is steady, invisible exposure, a physical condition of the planet itself. Yet despite all of this, Mars remains our nearest viable destination in the solar system. Not because it is ready, but because it has features that can be built upon. It has land to stand on, gravity that is low but workable, water locked in ice, resources in rock, and days roughly the same length as ours. The combination is rare. Among known worlds, Mars is the one that is difficult rather than impossible. A quiet human mirror fits here. We explore Mars because we can imagine adapting, even when the planet cannot. Another reflection arises naturally. Every challenge Mars presents is observable and solvable through engineering. Pressure can be created, heat can be generated, radiation can be shielded, water can be extracted. These are not theoretical obstacles, they are practical ones, the kind solved step by step. So the anchor fact becomes clear. Mars is uninhabitable by nature, but not by definition. And this is where our movement toward the planet begins. We choose Mars not because it welcomes life, but because it reveals what life can do. Mars became uninhabitable through a sequence of physical processes that unfolded slowly, each one weakening the planet's ability to hold warmth, water, and atmosphere. To understand why we are moving there despite these conditions, we need to trace the mechanism that shaped the world we see today. The explanation begins deep beneath its surface. Mars once had a warm interior. Early in its history, the planet produced heat through radioactive decay and leftover energy from its formation. This internal heat powered a magnetic field generated by the motion of molten metal. A magnetic field is not merely a planetary feature, it is a shield. It prevents charged particles from the Sun from stripping away atmospheric molecules. When Mars was young, this shield was active. But as the interior cooled, convection slowed, and the magnetic field weakened. Without it, the solar wind began removing the atmosphere, molecule by molecule. This was not a dramatic event. It was a long erosion, carried out by invisible particles. Over millions of years, the atmosphere thinned, pressure dropped, and water on the surface evaporated or froze into permanent ice. A small visual helps. Dust lifts from the plains, carried by winds that persist even in the thin air. The sky is dimmer than Earth's, the sun a sharper point. Light strikes the surface, but warmth cannot stay. Heat radiates upward and escapes into space. This is the mechanism that made Mars uninhabitable. A gradual cooling, a fading magnetic field, a thinning atmosphere, and the loss of stable water. Each element is measurable. Spacecraft instruments confirm the speed at which the atmosphere still escapes today. It is slow but continuous, like a planet breathing outward. To understand how this shapes the modern environment, consider the boundary between air and ground. On Earth, the atmosphere presses down with enough force to allow liquid water to exist across wide temperature ranges. On Mars, the pressure is less than 1% of Earth's. In such thin air, water does not behave the way we expect. It sublimates, jumping directly from solid ice into vapor. This is why astronauts cannot rely on surface water on Mars. Any exposed ice would vanish into the air. A micro-thought experiment helps. Imagine holding a cup of ice on Mars. As sunlight touches it, the surface begins to warm. But instead of forming droplets, the ice slowly turns to vapor, disappearing without melting. This is the physics of low pressure in action. Even simple behaviors of matter shift when the environment changes. Radiation adds to the mechanism. Without a strong magnetic field and thick atmosphere, high-energy particles reach the ground freely. This radiation alters chemical structures in soil and affects human cells. It also influences the search for life. Any microbes that once existed near the surface would have been exposed to this radiation for billions of years. That is why modern searches for Martian life focus underground, where soil and rock provide natural shielding. A reflection fits here. The deeper we investigate Mars, the more it reveals a world shaped by absence. No shield, no pressure, no liquid water. And yet each absence tells us something about how planets change over time. Now the mechanism of habitability becomes the mechanism of engineering. If Mars is uninhabitable because its atmosphere is too thin, then habitats must create their own internal pressure. If the surface loses heat quickly, structures must produce their own warmth. If radiation is constant, walls must absorb or deflect it. These solutions are physically straightforward but operationally complex. Another visual cue helps shape the scene. Inside a pressurized habitat, the air feels still. Outside, wind moves dust across plains that stretch for kilometers. Light filters through a pink-orange sky. The transparent walls of a greenhouse hold pressure against the vacuum, the structure swelling slightly outward. The difference between inside and outside is not philosophical, it is physical, continuous, measurable in every breath. Life support systems reflect this same mechanism. Mars is uninhabitable fundamentally because its environment does not support biological cycles. Earth relies on air, oceans, plants, and weather to keep oxygen and carbon dioxide in balance. On Mars, all of that must be replaced with machines that generate oxygen, recycle air, and store energy. The scale is smaller than Earth's systems, but governed by the same science. A subtle human mirror fits here. We are building pieces of Earth not to escape our world, but to understand how much of it is necessary for life. One more angle deepens the mechanism: soil. Martian soil contains perchlorates, compounds that interfere with biological processes. They are stable in cold, dry environments and require treatment before plants can grow. This introduces a step between raw resource and usable material. Extracting water from soil involves heating it, filtering it, then condensing vapor. This is not speculative. Experiments on spacecraft, including recent oxygen generation tests, demonstrate that these systems work on Mars. A brief analogy clarifies the challenge. Living on Mars is not like camping in a wilderness. It is more like living inside a research station at the bottom of an ocean trench. Every condition outside is incompatible with life. Every step depends on controlled environments. Yet, the station can function for years if systems are maintained and monitored. As we reach the end of this subphase, a larger insight emerges. Mars became uninhabitable through natural planetary evolution. We are moving there not because the planet is ready, but because its challenges can be mapped, measured, and engineered around. The mechanism that once stripped Mars of habitability now defines the blueprint for how we will live on it. We adapt not by changing Mars, but by understanding it precisely. The paradox of Mars begins with a simple conflict. Everything that defines the planet argues against human presence, yet everything we learn about it pulls us closer. Mars resists life, but it invites investigation. It rejects biological survival, but it reveals geological history in perfect clarity. It is a place where life cannot thrive, and yet a place where life's questions become easier to ask. This tension appears the moment we compare the two worlds. On Earth, life is everywhere, in oceans, forests, deserts, clouds, and even deep within rock. On Mars, no confirmed life exists on the surface. The contrast should push us away. Instead, it amplifies our curiosity. A lifeless planet becomes a controlled experiment in planetary evolution. It shows what happens when a world cools too quickly, loses its atmosphere, and shifts from wet to dry. It is a case study written on a global scale. A visual layer strengthens the feeling. Light slides across the rim of a crater, illuminating ancient layers of sediment. These layers formed billions of years ago, preserved with almost no disturbance. There is no rain to erode them, no vegetation to break them apart, no tectonic shifts to bury or uplift them. The planet stays still, and because it stays still, it keeps its memories. This is the paradox's first level. Mars is dangerous for humans, but ideal for science. Another layer appears when we consider time. Earth changes rapidly. Water flows, weather cycles. Erosion smooths landscapes. Biology reshapes ecosystems. Mars, by contrast, is slow. Processes stretch across immense spans. A single landslide can remain visible for millions of years. The dunes shift, but the underlying terrain holds its shape. Time moves differently on Mars, not because physics changes, but because activity slows. This disk here, a thought experiment helps. Imagine walking across a Martian plain. Every rock around you has been sitting in the same place for ages longer than human civilization has existed. The dust beneath your feet may have blown across the planet slowly, grain by grain, carried by thin winds over centuries. Nothing around you responds to your presence. The environment stays indifferent, calm, almost frozen in time. Now compare that with Earth, where life reacts instantly, plants bending toward light, animals adjusting movements, air thick with microorganisms. On Mars, nothing responds. This stillness can feel serene or unsettling, depending on how deeply you think about it. From this contrast emerges the second level of paradox. Mars is the closest world to Earth, yet it feels more alien than distant gas giants. We move deeper. Mars is uninhabitable because it lacks protection, warmth, and pressure, and yet those same conditions offer an unusual clarity when studying the planet's past. On Earth, life complicates geology. Biological activity alters rock, soil, and atmosphere. Mars, by lacking life, preserves raw planetary processes. It is a testbed for understanding how worlds form, evolve, and decline. A reflection fits naturally here. Mars reminds us that habitability is fragile. A small change in temperature, magnetic shielding, or atmospheric density can determine whether a planet grows forests or freezes deserts. Here comes the paradox's human side. We are drawn to Mars not because it welcomes us, but because it doesn't. A world indifferent to life forces precise thinking. It forces engineering. It forces clarity in what we require to survive. Every challenge becomes a mirror that shows us what life demands at the most fundamental level: pressure, heat, air, water, and stability. Mars makes these conditions visible by their absence. A visual cue rises again. In the thin light of Martian noon, shadows appear sharp. A habitat dome stands alone, its surface reflecting pale red. Around it, a vast silence stretches in every direction. No sound of insects, no rustle of leaves. Only wind, dust, and the low hum of machinery inside the structure. This silence deepens the paradox. Mars is quiet, but the work required to live there is constant. We can push the paradox further by considering long-term presence. Mars demands self-sufficiency. Supply missions from Earth take months and are limited by launch windows. Any settlement must recycle air, water, and materials with near-perfect efficiency. The planet that provides nothing becomes the place where we learn to waste nothing. Two opposing sentences sharpen the tension. Mars cannot support life. Mars may teach us how to support life elsewhere. Another paradox arises when we consider gravity. Mars has lower gravity, which reduces structural loads and makes lifting materials easier, but it also affects human biology, weakening bones and muscles over time. The benefit and drawback are intertwined. The same condition that simplifies construction complicates human health. A micro-story helps anchor this. An astronaut exercises inside a rotating gym module. The equipment is designed to counteract bone loss. Outside, the landscape is still. Dust drifts across the horizon. The planet assists the work of building through lighter gravity, even as it makes maintaining a human body more difficult. This creates a subtle insight. Mars gives and takes in the same motion. As we approach the close of the subphase, the paradox converges into a single idea. Mars is uninhabitable in the natural sense, yet fully accessible in the engineered sense. It becomes a place where survival is not a gift of the environment, but a direct outcome of knowledge. The planet does not change for us. We change our surroundings within it. And this leads to the deepest paradox of all. By moving to a world where life cannot exist unaided, we learn what part of life is essential and what part is optional. The boundary between nature and technology dissolves. A habitat becomes an ecosystem. A machine becomes an organ of survival. A settlement becomes a controlled version of home. Mars remains uninhabitable, and yet, through understanding, it becomes livable in fragments. Knowledge becomes the bridge between an uninhabitable world and a livable future. Not by transforming Mars into something it isn't, but by understanding its conditions deeply enough to work within them. The more precisely we measure what Mars lacks, the more clearly we see what must be constructed, protected, or generated. In this sense, knowledge is not abstract. It is a survival tool. We start with the fundamentals. To live on Mars, people will depend on systems that replicate Earth's essential conditions inside controlled environments. These systems already exist in prototypes. They produce oxygen from carbon dioxide, recycle water from humidity and waste, and maintain pressure through durable, flexible materials. When engineers test these systems, they are not speculating. They are rehearsing the physics of survival. A visual cue anchors the idea. Inside a small laboratory on Mars, a transparent cylinder glows faintly. Inside it, carbon dioxide drawn from the thin atmosphere is split into oxygen and carbon monoxide. The oxygen collects in a reservoir. It is a small amount, but it is proof of principle. Even on an uninhabitable world, the elements required for life can be rearranged through knowledge. This leads to an important insight. Mars is uninhabitable naturally, but not chemically. The elements needed for water, air, and fuel exist there. What is missing is the environment that organises them. Knowledge fills this organisational gap. We can extend this idea to energy. Mars receives less sunlight than Earth, but its skies are clear for long stretches. Solar arrays produce power efficiently during the day, supported by batteries that store excess energy for the cold nights. When dust storms reduce sunlight, reactors or other backup systems provide stability. None of this relies on the planet being habitable. It relies on understanding how to convert Mars's conditions into reliable energy cycles. The subtle human mirror fits here. We survive not because Earth provides everything, but because we learned how Earth works. Mars simply demands the same process in a new setting. Now consider water. Mars hides water in ice, soil, and minerals. The challenge is not finding it, but extracting and processing it. Heating ice to create vapor, condensing it, filtering it, and storing it. These steps replicate natural cycles that once occurred on Mars billions of years ago. Human technology reintroduces processes the planet lost. A micro-thought experiment illustrates this. Imagine a robotic rover drilling into icy ground. As the drill turns, fragments of frozen soil rise into a chamber. A heater warms the samples, releasing vapor. The vapor condenses inside a small metal coil, forming droplets that fall into a container. These droplets may have been locked in ice for millions of years. Now they become part of a human water supply. This isn't magic. It is physics applied carefully. Knowledge also clarifies the constraints. Radiation remains a constant threat. Structures must be buried beneath layers of soil or shielded with materials that absorb high-energy particles. Greenhouses may require transparent protective layers combined with angled surfaces that reduce exposure. These solutions emerge from precise measurement of radiation levels across the Martian day and year. A reflective line fits here. The more accurately we see a world, the more livable it becomes. Another core insight connects past and future. Mars shows us what happens when a planet loses its protection. Earth once faced similar threats: solar storms, atmospheric changes, magnetic reversals. Studying Mars helps us understand our own planet better. In this sense, Mars is both a destination and a teacher. Now the knowledge deepens into a conceptual shift. Habitability is not a binary state. It is a gradient shaped by conditions, resources, and technology. A world can be uninhabitable for natural life, but habitable for engineered life. This realization reframes the entire question of moving to Mars. We are not relocating to a second Earth. We are expanding the definition of where humans can exist. At this point, two opposing sentences bring clarity. Mars will never be Earth. But Earth is not the only place where life can take root. The paradox that dominated the earlier subphase now stabilizes into understanding. Mars remains uninhabitable, but the tools required to live there are advancing rapidly. Every lander, orbiter, and rover adds knowledge. Every experiment that turns air into oxygen or ice into water reduces uncertainty. Every simulation of habitat pressure or radiation shielding transforms impossibility into engineering. A visual cue reinforces this stability. In a dim Martian dusk, lights inside a habitat glow softly. They reveal a space maintained at constant temperature, filled with breathable air, recycled water, and growing plants. Outside, the land is cold and silent. Inside, the environment follows rules written by knowledge, not by Mars. This moment sets up a final insight for the subphase. Life on Mars will be an ongoing negotiation between biology and environment. It will require constant monitoring, adjustment, and maintenance. Systems will need redundancy. Habitats will evolve over time. But these challenges do not diminish the possibility. They define it. A final reflection prepares the next block. We are not trying to make Mars comfortable. We are learning how to sustain life under conditions that differ from everything in our evolutionary history. And so the knowledge solidifies into a single line, quiet and stable. Mars does not become habitable for us. We become knowledgeable enough to inhabit Mars. Mars is uninhabitable for humans, yet in every current mission plan, Mars is the next place we intend to live. This contrast becomes sharper when we examine one anchor fact. Mars offers stability in its geology, even as it denies stability in its environment. The land itself barely changes. The atmosphere changes constantly. The surface preserves history. The climate erases nothing but warmth. This mixture of permanence and instability shapes every future settlement. Consider the ground beneath future habitats. Martian rock is ancient, often billions of years old, untouched by rain or vegetation. Its surface holds craters that formed before multicellular life evolved on Earth. Erosion occurs but slowly, grain by grain, guided by thin winds. Structures built on this ground rest on a planet whose surface rarely shifts. In this sense, Mars is predictable. A visual cue anchors this. Morning light hits the edge of a crater wall, revealing layers stacked like pages of a silent record. Nothing stirs, except dust carried by a gentle wind. The ground is quiet, steady, unmoving. A foundation more stable than many places on Earth. But the air above this ground tells a different story. Temperatures swing widely between day and night. Dust storms rise suddenly, sometimes covering the entire planet. Radiation levels shift with solar activity. Pressure remains so low that a puncture in a habitat wall would release air in seconds. The land is stable, but the environment is volatile. This tension forms the core of the anchor fact. Mars provides a foundation for building, but not for living. Everything above the ground must be engineered. A micro-story helps illustrate the contrast. Imagine an early Mars mission. Engineers land a small robotic construction unit. Its task is simple: test anchoring systems for future habitats. The robot drills anchor rods into the ground. The soil is firm, compacted by eons of stillness. The anchors hold perfectly. But, as night falls, the unit's electronics experience a sharp temperature drop. Its internal heaters activate. Frost forms on exposed parts. The ground remains unchanged. The environment shifts dramatically. The robot is stable only because its systems can adapt to the cold. This is the same balance human habitats must strike. Stability from below, resilience above. Another reflection appears naturally. On Earth, environments are dynamic, but life adapts biologically. On Mars, the environment is harsh, but the ground is steady. The stability we need is present, but not in the form we're used to. The anchor fact expands further when we consider resources. Mars has water ice locked below the surface. It has carbon dioxide in the air. It has basaltic rock that can be refined into metals and ceramics. The challenge is not the absence of materials, but the absence of conditions under which these materials naturally support life. This difference is subtle but important. A world can be uninhabitable and still resource-rich. A visual cue shifts the scale. In low sunlight, the horizon glows faintly. A layer of ice lies just beneath the surface, revealed by robotic drills. The ice looks inert, but it represents a reservoir of future drinking water, oxygen, fuel, and even building material. The land holds potential. The air offers none. From here, a natural reflection emerges. We often think of habitability in terms of comfort. Mars reframes it in terms of access. Water, minerals, sunlight, heat sources. These resources exist, but in forms that require technology, not biology. Consider the length of a Martian day. At just over 24 hours, it matches Earth closely. This small detail becomes another anchor. Every system relying on daily cycles, energy, agriculture, circadian rhythms, can run in patterns similar to Earth. In contrast, the thin atmosphere forces constant vigilance. Internal lighting, pressure, and temperature must stay stable regardless of what happens outside. Two opposing sentences clarify the idea. Mars gives us a familiar rhythm. Mars gives us nothing else. We can see the paradox of environment and foundation clearly in how habitats will be built. Most plans involve partially burying structures beneath soil, using the planet's stable ground as natural shielding. The dirt overhead protects against radiation, The stable terrain prevents shifting. Humans rely on the ground, but must recreate atmosphere. Mars provides one half of the equation. The other half must be imported or constructed. A thought experiment sharpens this idea. Picture a future settlement beneath several meters of soil. Inside, plants grow under carefully calibrated lights. Air circulates through filters. Water flows through pipes warmed by the habitat systems. Outside, the land is silent. There is no temperature regulation, no natural insulation. The structure survives because the ground is reliable, while everything else inside resists the external environment. This division defines life on Mars. Support comes from what does not change. Survival comes from building what must change. As we approach the close of the subphase, a final insight emerges. Mars is uninhabitable not because it lacks resources, but because it lacks processes. There is no weather to distribute heat, no magnetic field to block radiation, no hydrological cycle to sustain water flow, no biological system to recycle air. But the physical foundation exists. The land is steady, the resources are present, the planet is mapped, measured, and reachable. Mars does not offer habitability, but it offers consistency, the one thing engineering thrives on, and so the anchor fact lands with calm clarity. Mars cannot sustain life naturally, but it can support everything we build to sustain life. To understand how humans will actually live on Mars, we need to examine the mechanisms that turn an uninhabitable world into a functional settlement. These mechanisms are not speculative. They come from physics, chemistry, engineering, and environmental science, each one addressing a gap left by the planet's natural conditions. The first mechanism is pressure control. Mars's air is so thin that liquid water is unstable and human lungs cannot function. Inside habitats, pressure must be maintained close to Earth-like values. This requires strong shells, flexible seals, and constant monitoring. If pressure drops even slightly, sensors detect the change immediately. Automated systems close valves and reroute airflow. Living on Mars means living inside a pressure envelope shaped entirely by technology. A visual cue helps fix this in the mind. A habitat dome sits on the plane, slightly bulging outward because internal pressure exceeds external pressure. When sunlight passes across its surface, the dome glows faintly. Inside, air remains dense and warm. Outside, the atmosphere is almost empty. The second mechanism is atmospheric processing. Mars's air is mostly carbon dioxide. Machines pull this in and convert it into oxygen using electrochemical reactions. Other systems remove traces of dust and CO2 buildup inside habitats. Each part functions like an artificial biosphere, taking the place of plants, oceans, and atmospheric cycles that do not exist on Mars. This leads naturally to the third mechanism, thermal regulation. Mars's environment can drop tens of degrees within hours. Structures need multi-layer insulation, heating coils, and thermal mass to store warmth through the night. These systems must balance carefully. Too much heat increases pressure, too little compromises survival. A short reflection fits. On Earth, warmth is a background condition. On Mars, warmth is an engineered state. Now we move to radiation shielding, one of the most critical mechanisms. Without a strong magnetic field, Mars exposes everything on its surface to cosmic rays and solar particles. Shielding works through materials that absorb or deflect these particles: soil, plastic composites, water, or metal layers. Many settlement plans place habitats underground or cover them with several meters of regolith. A micro-thought experiment illustrates this. Imagine a narrow habitat tunnel carved into the side of a small hill. Above it sits a thick layer of soil, piled intentionally to block radiation. Inside the tunnel, light panels illuminate walls lined with equipment. Plants grow under bright LEDs. Air circulates quietly. The soil above has no life, but it protects the life below. Another mechanism deals with water extraction and recycling. Water exists on Mars mostly as ice. Robots mine icy soil, heat it, capture the vapor, and condense it. Once water enters the settlement, it is recycled repeatedly. Showers, plants, humidity, and even waste become sources of reclaimed water. Closed-loop systems reduce losses to nearly zero. The concept is simple. Nothing leaves unless absolutely necessary. A visual cue marks this clearly. In a dim engineering bay, a thin stream of condensed water drips into a container. Every drop represents the planet's ancient ice. unlocked through heat and pressure. Energy is the mechanism tying all others together. Solar power works efficiently on Mars because the atmosphere is thin, allowing more direct sunlight to reach panels. However, dust storms can reduce sunlight for weeks. Backup nuclear reactors provide stable power during these periods. Batteries smooth daily cycles, storing energy during peak sunlight and releasing it at night. A reflection arises naturally. On Mars, energy is not just a utility, it is the underlying condition for life. Agriculture introduces a new set of mechanisms. Plants need controlled pressure, temperature, humidity, and light. Greenhouses likely operate under reduced pressure to reduce structural stress, with oxygen-rich air circulating through them. Soil may come from processed Martian dirt mixed with organic material created inside the habitat. LEDs tuned to specific wavelengths drive growth efficiently. This creates an interesting reversal. On Earth, plants create environments for animals. On Mars, environments must be created for plants. Each mechanism is interdependent. Pressure systems affect oxygen production. Thermal systems affect water recycling. Radiation shielding affects habitat placement. Energy availability affects every subsystem simultaneously. This interdependence forms a network, a synthetic ecosystem designed to replace natural planetary processes. Now consider mobility, another mechanism of survival. Mars's gravity is lower, making movement easier but affecting human physiology. Vehicles must be pressurized, insulated, and radiation shielded. Rovers recharge using solar panels or direct power lines at settlements. Walking outside requires full suits that provide pressure, air, and thermal control. A single tear in a suit becomes life-threatening, so suits must detect damage instantly. A microstory highlights the mechanics. An astronaut drives across a plain toward a sample site. The rover's sensors monitor wheel traction, radiation levels, internal pressure, and battery charge. When a gust of wind lifts dust across the road, visibility drops. The rover compensates with navigation sensors that read terrain contours. The astronaut sits comfortably inside, but everything around them, pressure, heat, sound, is artificial, created by engineering. As we approach the end of this subphase, an insight becomes clear. Every mechanism that supports life on Mars replicates something Earth provides naturally. Mars forces these systems to be explicit. It makes us articulate the invisible processes we take for granted. Two opposing sentences capture this shift. Mars cannot sustain us automatically, but it can sustain us mechanically, and a final visual cue draws the subphase to its quiet ending. In the evening, settlement lights illuminate a cluster of domes and tunnels. Machinery runs softly. Beyond the structures, the land lies cold and silent under a thin orange sky. Everything outside resists life. Everything inside preserves it. Life on Mars does not emerge from the planet. It emerges from the mechanisms we build. The paradox at the center of Martian settlement deepens when we examine how humans interact with their environment. On Earth, life shapes the planet, carving rivers, altering air, and creating soil. On Mars, the relationship reverses. Mars forces us to adapt entirely, yet gives nothing in return. It is a world where survival depends on understanding limits rather than expanding into opportunity. This begins with a simple contradiction. Mars demands complete protection from its environment, but also complete exposure to its conditions for scientific exploration. Astronauts must leave safe habitats to study geology, search for ancient water, and test resources. Each step outside increases risk. Exploration requires vulnerability. Survival requires insulation. These two goals conflict constantly. A visual cue amplifies the contradiction. The suited astronaut stands at the edge of a canyon carved by ancient water. The rock layers glow in the thin sunlight. Behind the astronaut, a pressure suit hisses quietly, maintaining life. The canyon invites discovery. The suit enforces distance. Curiosity pulls forward. Safety pulls back. This is the paradox of exposure. To understand Mars, we must enter the very environment that makes it uninhabitable. It grows sharper when we consider scale. Mars is vast, with deserts, volcanoes, and canyons that dwarf their earthly counterparts. But the zones where humans can live are tiny. Sealed habitats, tunnels, and pressurized vehicles. The planet is enormous. Our presence is microscopic. A settlement may spread across a few kilometers, but the surrounding landscape stretches across millions. A reflection fits naturally. We live large on Earth. On Mars, we will live small. Even gravity contributes to the paradox. Lower gravity makes lifting, building, and transporting materials easier. Structures can span wider distances without collapsing, but the same low gravity weakens human bones and muscles. The environment simplifies engineering while complicating biology. Two opposing sentences make the tension clear. Mars is gentle on machines. Mars is harsh on bodies. This tension mirrors another contradiction. The planet is deadly at the surface but potentially safe underground. The soil offers natural radiation shielding, stable temperatures, and structural support. Yet humans instinctively associate life with open landscapes and sky. On Mars, the places most suitable for living are the ones most removed from instinctive notions of habitation. Underground tunnels may become the safest homes, even though they separate settlers from the landscape they travelled to see. A microstory illustrates this contrast. Inside an underground habitat, warm lights illuminate smooth walls carved by robotic drillers. Plants grow in controlled pods. Humidity is steady. The air is warm. Outside, frost forms on exposed rock. The temperature drops rapidly. The sky fades into a deep orange grey. The habitat feels alive. The surface feels frozen in time. This creates a quiet paradox. The safest part of Mars is the part we cannot see. Another paradox arises in the realm of resources. Mars is uninhabitable, yet rich in essential materials: water ice, metal-bearing rock, carbon dioxide for oxygen production. The ingredients for survival exist, but none are accessible without significant energy and machinery. The planet holds everything we need, but nothing is offered freely. A reflection emerges. On Earth, resources shape life. On Mars, life shapes the usefulness of resources. Now we confront one of the deepest paradoxes of Martian settlement. Mars teaches us about Earth by being nothing like it. Its thin atmosphere reveals how important pressure is. Its cold climate demonstrates the fragility of heat. Its radiation exposure shows the value of magnetic shielding. Every challenge on Mars becomes a lesson in planetary habitability. Lessons we apply not only to Mars, but to our understanding of Earth's future. Here, a visual cue reinforces this idea. The thin Martian horizon glows faintly as the sun sets. The temperature plunges. The sky loses colour within minutes. The world feels distant, unprotected. Watching this from inside a pressurized window, a human sees Earth more clearly because Mars removes everything that Earth provides naturally. This paradox ties into another. Mars is inaccessible in everyday terms, far away, dangerous, resource poor. Yet technologically, it is more accessible than the deep oceans, Venus, or even many regions of Earth's own interior. We can land there, operate machines, and send data back within minutes. The planet that cannot host life is the one that most readily hosts machines designed to support it. A subtle human mirror fits here. We travel so far to learn what we need to protect close to home. As this subphase nears its end, the paradox converges into one unifying tension. Mars demands careful engineering, but engineering alone is not enough. Knowledge must anticipate failures. Systems must overlap. Survival is not guaranteed by any single device, but by networks of processes working together. The more complex these systems become, the more they resemble ecosystems, not natural but synthetic. Two opposing ideas clarify the final insight. Mars requires independence from the environment. Mars forces dependence on every system we build, and here the paradox settles into a single quiet line. Mars resists life completely, yet reveals what life requires with perfect clarity. Knowledge is what transforms Mars from a distant, hostile world into a place where humans can live deliberately. Not comfortably, not easily, but deliberately, with clarity about every condition we must replicate. The planet does not bend to biology. Biology must bend to physics, chemistry, and engineering. This is the foundation of Martian knowledge, understanding what life needs so precisely that those needs can be rebuilt rather than assumed. We begin with the idea of controlled environments. On Earth, life thrives within narrow limits: pressure, temperature, oxygen concentration, humidity, radiation. These limits are invisible in daily life because Earth maintains them automatically. On Mars, none of these parameters exist in life-supporting ranges. Knowledge becomes the system that replaces natural balance. Engineers design habitats by measuring the exact tolerances of the human body and building systems that maintain those tolerances minute by minute. A visual cue anchors this idea. Inside a habitat, a display panel shows pressure, temperature, oxygen levels, and carbon dioxide concentration. Each number updates in real time. Outside the panel's window, dust blows across barren ground. Inside, the numbers remain stable because knowledge holds them there. The next layer of knowledge concerns closed-loop systems. On Earth, water cycles through evaporation, condensation, and groundwater flow. Air cycles through plants, oceans, and geology. On Mars, these cycles do not exist. Instead, machines replicate them with precision. Water recycling systems capture moisture from the air, reclaim it from waste, filter it, and return it to use. Air systems convert carbon dioxide into oxygen, scrub contaminants, and maintain circulation. A reflection fits naturally. Mars shows us that life depends not on abundance, but on cycles. And cycles depend on understanding. Energy knowledge follows. Mars receives sunlight, but with lower intensity and periodic dust storms. Engineers analyze patterns of light, shadow, and dust loading. They determine panel angles, storage capacities, backup sources, and load management. Knowledge becomes the architecture behind every watt used in a habitat. A micro-thought experiment helps clarify this. Imagine a dust storm that reduces sunlight for 3 weeks. Solar power drops dramatically. Batteries drain steadily. A nuclear reactor or other backup source activates, keeping life support systems running. Every step, the detection, the transition, the stability, follows knowledge embedded in systems that anticipate the planet's behavior. The next layer is geological knowledge. Humans will rely on Martian rock for construction materials, radiation shielding, and mineral extraction. But Martian soil contains perchlorates, chemicals that interfere with biology. Understanding how to remove or neutralize them becomes essential for agriculture. Robots will analyze soil composition region by region, mapping usable and unusable zones. Knowledge turns raw terrain into meaningful resource. A visual cue strengthens the point. A robotic arm digs into reddish soil. Sensors analyze the sample. A small screen lights up with the chemical composition. The soil is not ready for plants. It must be treated, processed, transformed. Knowledge turns inert dust into a future substrate for growth. Now the concept deepens. Knowledge becomes the environment. On Mars, survival depends not on climate or atmosphere, but on systems built from data. A habitat's climate is a designed climate. Its atmosphere is an engineered atmosphere. Its water cycle is a manufactured cycle. The environment inside is not Martian or Earth-like. It is informational, shaped by feedback loops, sensors, algorithms, and human oversight. Two opposing sentences capture this transition. Life on Earth evolves to fit the world. Life on Mars requires the world to evolve to fit life. This distinction drives the next insight. Mars teaches us how much of Earth's environment is fragile. The planet removes everything we take for granted: stable air, protective magnetism, liquid water, balanced heat, leaving only the fundamentals of planetary physics. By studying these stripped-down conditions, we learn which elements of Earth sustain life and why. Mars becomes a mirror that clarifies Earth's uniqueness. A human mirror line fits quietly here. When we understand Mars, we understand ourselves with more precision. Another dimension of knowledge arises from biology in isolation. Plants grown on Mars will rely entirely on engineered light, water, and soil. Their growth patterns will reveal how tightly life depends on external environment, and how much can be tuned or optimized. Humans living in reduced gravity will provide new data on bone density, muscle adaptation, and long-term physiology. Mars becomes a natural experiment in understanding the limits of human biology. A micro-story illustrates this. Inside a greenhouse, a row of plants grows beneath bright lights. The leaves move slightly as air circulates. Sensors measure moisture in the soil, oxygen output, and nutrient levels. Outside, the air is too thin for any plant to survive even seconds. But inside, Plant growth becomes a demonstration of knowledge overcoming environment. As this subphase nears completion, the final insight emerges. Knowledge allows life to exist where conditions forbid it, not through defiance, but through precision. Mars remains uninhabitable in every natural sense, yet increasingly livable in every engineered sense. Settlements become nodes of understanding, islands of Earth-like conditions, maintained by constant attention. Two final opposing sentences bring the idea to stillness. Mars is uninhabitable by nature. Mars becomes habitable through understanding. A visual cue closes the subphase gently. Night falls. The temperature drops sharply. The land cools in minutes. Yet, inside a habitat, lights glow softly. Condensation forms on the walls of a water recycler, and oxygen flows into the air. The environment exists not because Mars provides it, but because knowledge sustains it. On Mars, survival is not a condition of the planet. It is a condition of what we know. The next anchor fact begins with a truth that feels almost understated. Mars is the closest world where humans can build a permanent presence, yet it is the farthest distance at which human life has ever been sustained. This distance shapes everything: travel time, communication, supply lines, psychological resilience, and the design of settlements meant to function with months of isolation. To understand why this distance matters, consider the scale. At its closest, Mars is still tens of millions of kilometers away from Earth. Signals take several minutes to travel in each direction. A question sent from Mars to Mission Control may not receive an answer for nearly half an hour. For astronauts, this delay transforms operations. They cannot rely on instant instruction or immediate help. On Mars, autonomy is not a preference, it is a requirement. A visual cue anchors this idea. Inside a small control room on Mars, a crew member sends data back to Earth. The screen displays a transmission light that blinks slowly. Outside, the landscape is silent. The message will take minutes to reach its destination. Decisions made during emergencies must rely on local knowledge, not distant guidance. This distance affects logistics too. Supplies launched from Earth take half a year or more to arrive. Launch windows open only when Earth and Mars align in orbit, roughly every 26 months. A missing tool, a late shipment, or an unexpected malfunction cannot be fixed by immediate resupply. Settlements must store redundancies, repair equipment on site, and recycle materials indefinitely. A micro-story captures this constraint. A habitat's air filter fails unexpectedly. On Earth, replacement parts could arrive in days. On Mars, the crew must either repair the filter with available components or use backup systems designed for emergencies. Every tool, every spare part, every gram of material must either be brought from Earth or manufactured locally. The planet's distance forces a new kind of self-reliance. This leads to an important anchor point. Mars is uninhabitable, but it is also unforgivingly remote. Survival requires independence from Earth. Knowledge and adaptability become daily necessities. The psychological dimension grows from this same fact. Humans evolved in environments defined by immediate feedback, nearby communities, rapid communication, familiar landscapes. On Mars, the sky is alien, the distance is vast, and the horizon feels both close and empty. Crew members must maintain mental stability in an environment that provides no natural reassurance. A reflection fits naturally. On Earth, we feel connected simply by walking outside. On Mars, stepping outside increases isolation. Distance shapes exploration too. Every rover on Mars today operates through delayed commands. Human explorers will face a different but related challenge. They will be present on the surface, but unable to coordinate instantly with Earth-based science teams. Decisions about what to sample, where to drive, and how long to explore must be made with autonomy and discipline. The delay turns every scientific activity into a test of planning. Now consider the anchor in terms of settlement architecture. A Mars base cannot function as an outpost waiting for Earth's support. It must operate like a remote research station, capable of months of sustained isolation. Power, food, oxygen, water, and spare parts must originate locally. This transforms settlement design into a system of interlocking redundancies. Every failure has at least two backups. Every backup has its own fallback plan. A visual cue reinforces this structure. In the early morning, the lights of a Martian settlement flicker on. Solar arrays adjust their angle to the rising sun. Inside, water flows through recycling circuits. Seeds grow under artificial lights. Nothing comes from Earth at that moment. Everything exists because the systems work. This brings us to a deeper anchor fact that ties distance to survival. Mars forces us to design habitats as ecosystems rather than buildings. A building fails and can be repaired later. An ecosystem fails and must be corrected instantly. Every part interacts with every other. Water recycling affects air quality. Energy availability affects temperature. Storage capacity affects agriculture. The distance from Earth demands a closed circle, not a supply chain. A micro-thought experiment illustrates this interdependence. Imagine a crew of 6 living inside a settlement. One system briefly slows, oxygen production dips. Within seconds, sensors detect the change. Ventilation adjusts. A backup unit activates. Earth will know only after the crew reports it. The response happens locally, directed by knowledge and automated systems working in unison. This constraint also shapes exploration strategy. Mission planners assume not only that problems will arise, but that they must be solved without Earth's help. In this way, distance becomes both a risk and a training ground. Mars teaches resilience by requiring it. At this point, 2 opposing sentences bring clarity. Mars is close enough to reach. Mars is far enough to be alone. A subtle reflection emerges. Living on Mars means understanding that help is not immediate. Safety comes from preparation, not proximity. This anchor fact also reframes human identity. For the first time, people will live on a world where Earth is a distant light in the sky, not the environment beneath their feet. This changes the way settlers perceive themselves. They are not travelers, but inhabitants of a world where life must be built daily, not assumed hourly. A final visual cue settles the subphase. Night falls on Mars. The sky darkens rapidly. A faint blue glow appears above the horizon as starlight reflects off dust. In the distance, Earth is a tiny point of light, visible but silent. Inside the habitat, humans breathe air made by machines, drink water melted from ancient ice, and speak to Earth with a delay that becomes routine. And the anchor fact becomes clear, steady, quiet. Mars is uninhabitable and far, a combination that demands independence, precision, and a new way of living. To understand how humans will operate on a world so distant and inhospitable, we need to examine the mechanisms that allow a settlement to function independently. These are not single systems, but networks of processes that together replace everything Earth naturally provides. On Mars, the mechanisms of daily life intertwine with the mechanisms of long-range communication, manufacturing, repair, and resilience. We begin with communications. Because signals take minutes to travel between Earth and Mars, software and systems on Mars must operate with autonomy. Automated diagnostics run continuously, checking oxygen generation, water recycling, power distribution, and structural integrity. If something deviates from expected values, the system does not wait for Earth. It reacts immediately. Humans intervene only when the system requests input. A visual cue brings this to life. Inside a small engineering bay, a screen displays a series of green indicators. One turns yellow, a pressure valve opening slightly slower than expected. Within seconds, the system reroutes airflow, isolates the valve, and activates a backup. A quiet notification appears for the crew. Earth will learn about it later, but the mechanism has already taken action. Next comes local manufacturing, essential because resupply is slow and expensive. Mars settlements depend on the ability to fabricate parts with available materials. This includes 3D printing components using Martian regolith mixed with imported or synthesized binders, forging metal extracted from local ore, and repairing equipment with modular pieces designed for easy replacement. A micro-story illustrates this. A rover's wheel tread wears down after months of traversing rocky terrain. Instead of ordering a new wheel from Earth, the crew retrieves spare segments printed on site from regolith-based composite. They fit the new segments onto the wheel, run diagnostics, and release the rover back into service. Distance means maintenance is not a temporary activity. It is a core mechanism of survival. The next mechanism is autonomous agriculture. Plants grown in Martian greenhouses depend on precise nutrient delivery, humidity control, and artificial lighting. Growth cycles are monitored by sensors that track soil moisture, carbon dioxide consumption, and leaf health. These sensors trigger adjustments automatically, increasing light, altering water flow, or adding nutrients. The mechanism reduces human labor while ensuring stability. A reflection emerges. On Earth, food grows through ecosystems. On Mars, food grows through data. Energy management forms another critical mechanism. Since the settlement must survive dust storms, night cycles, and seasonal changes, energy systems operate like a heartbeat. Solar panels track the sun, batteries fill and drain according to predicted loads, reactors provide baseline power. Algorithms forecast energy use days ahead, adjusting consumption to ensure life support always has priority. A visual cue enriches the scene. During a late afternoon, long shadows stretch across solar arrays. Panels tilt slightly, tracking the sinking sun. Inside a central control unit, graphs shift gently as power flows into the battery banks. When night arrives, the system transitions seamlessly to stored power. Humans do not feel the change. The mechanism holds the environment steady. Next is extravehicular activity management, the systems that control operations outside the habitat. Spacesuits are miniature life support units with internal pressure, temperature control, and oxygen recycling. Before every excursion, suits run automatic self-tests. If a sensor detects microscopic damage or pressure irregularity, the system locks itself out until repairs are made. A micro-thought experiment clarifies their importance. An astronaut walks across the plains toward a drill site. The suit compensates for temperature swings, filters carbon dioxide from the internal air, and maintains proper pressure against the near vacuum outside. If radiation levels spike momentarily, something instruments can detect. The suit alerts the wearer and recommends returning to shelter. Safety is not left to perception. It is built into mechanism. Now we move to habitat integrity, perhaps the most complex system on Mars. Habitats rely on multi-layered shells, internal scaffolding, and pressure-resistant materials. They contain sensors that monitor strain, detect microleaks, and analyze vibration patterns caused by movement or temperature change. If a small leak forms, the habitat can isolate the affected section, stabilize pressure, and seal the breach. A visual cue grounds the description. Inside a habitat corridor, a warning light glows softly. A tiny drop in pressure has been detected. Automated doors close in segments. A repair drone scans the outer wall. The breach is found. A small puncture caused by wind-driven debris. The drone patches it within minutes. The pressure stabilizes. The mechanism restores normal operation. Next comes the mechanism of redundancy. Because Mars is unforgivingly remote, every life support system includes multiple backups. Oxygen generators come in pairs, water recycling units have reserve pumps, heating systems include emergency heaters. Even habitat walls have redundant layers designed to maintain pressure if one layer fails. Redundancy transforms risk into probability management. A reflection fits. On Mars, reliability is not the absence of failure. Reliability is the ability to continue functioning when failure occurs. Finally, we reach mobility networks, pressurized rovers, drones, and autonomous cargo carriers that move supplies across the surface. These systems rely on navigation algorithms that read the terrain, avoid hazards, and adapt to dust conditions. Since signals from Earth cannot guide them in real time, these vehicles act independently, retrieving samples, mapping resources, and delivering cargo between locations. A visual cue completes the mechanism. A cargo rover drives across a barren plain at dawn, headlights slicing through thin dust. It carries spare parts to a distant outpost. No one drives it. No one supervises it in the moment. It follows a route generated by onboard sensors, guided by terrain models built from earlier explorations. It knows where it is going because knowledge embedded in software allows it. As this subphase closes, the mechanisms align into a single insight. Life on Mars depends on systems that think, act, and adapt before humans can respond. The planet's distance makes autonomy mandatory. The environment makes precision essential. The combination forms a new kind of living, one supported by mechanisms that weave technology into every breath. And the idea settles with calm clarity. On Mars, survival is not reactive. It is engineered into the mechanisms that operate long before danger arrives. The paradox of distance becomes sharper when we examine how human presence interacts with Martian isolation. Mars is the closest world where humans can live, but also the place where human life becomes most fragile. This fragility is not emotional or symbolic, it is operational. Every action on Mars depends on a system that must succeed, even when Earth cannot intervene. This leads to the first layer of paradox. Mars forces self-reliance, yet everything built there originates from Earth. Materials arrive from Earth, knowledge comes from Earth, designs are based on Earth's physics. Even the oxygen generated inside a habitat is produced by systems whose concepts were tested on Earth. Mars demands independence while enforcing dependence on a planet millions of kilometers away. A visual cue sets the tone. In a quiet Martian lab, a technician repairs a water filter. The design is Earth-made. The tools were launched from Earth. The training occurred on Earth. And yet, the repair must succeed far from Earth, without Earth's assistance. The technician works alone, in a place shaped entirely by a world they cannot reach quickly. This brings a reflection. We survive on Mars through systems we built on Earth, operating in a place where Earth cannot protect us. A second paradox emerges from communication. The delay between Earth and Mars slows conversation, but speeds autonomy. Because guidance cannot arrive instantly, settlers must think clearly, decide quickly, and solve problems alone. The distance makes them more competent, more aware, and more careful. Mars reduces connection in order to sharpen capability. Two opposing sentences crystallize this tension. Mars isolates humans physically. Mars strengthens humans mentally. Another paradox forms around risk. On Earth, danger often comes from unpredictable environments, earthquakes, storms, floods. On Mars, danger comes from predictable physics, vacuum, radiation, pressure loss, cold. These conditions do not change suddenly. They do not fluctuate wildly. They are consistent. The threat is ever present but rarely surprising. A micro-thought experiment clarifies this. Imagine stepping outside in a suit. The pressure outside remains near zero. The temperature is known. Radiation levels have been measured for years. Nothing unexpected appears. And yet every moment is dangerous because predictable conditions remain incompatible with human biology. Danger on Mars is constant, not erratic. This generates a paradox of stability. Mars is predictable, but unsafe. Earth is dynamic, but protective. Even agriculture carries its own paradox. Plants grown on Mars will rely on engineered environments. The control is total. Temperature, humidity, light, nutrients. But the outcome is fragile. A single malfunction could disrupt the entire cycle. Earth's ecosystems are messy but resilient. Martian agriculture is precise but delicate. Life succeeds through control, not abundance. A visual cue strengthens this feeling. Inside a greenhouse, bright lights illuminate rows of leafy plants. Each plant grows because sensors maintain ideal conditions. Outside the greenhouse, the land is barren and silent. Life thrives through precision. Life ends without it. Now consider the emotional paradox. Mars expands human presence beyond Earth, yet shrinks the world of those who live there. On Earth, stepping outside connects people to vast environments, sound, movement, weather, life. On Mars, stepping outside requires a suit and offers only stillness. The expansion of human reach leads to a contraction of sensory experience. A reflection fits here. Mars gives humanity a larger footprint, but gives individuals a smaller world. This leads to the cultural paradox. Mars represents exploration, adventure, and frontier, but the reality of living there is routine, careful, and methodical. Excitement lies in leaving Earth. Daily life on Mars resembles maintaining a research station, structured, disciplined, and centered around reliability. Two quiet sentences emphasize this. We travel to Mars for discovery. We stay there for maintenance. A deeper paradox arises when considering identity. Humans evolved under Earth's sky. Our biological cycles match Earth's rhythms. But Martian settlers will see Earth as a point of light, not a landscape. Their home becomes a place they cannot reach quickly. Meanwhile, the world they stand on is uninhabitable without constant support. This produces a subtle shift. People on Mars will belong to a world that does not support them. A visual cue reinforces this. A settler looks through a thick window at the Martian horizon. The sky is thin and pale. The land is vast but empty. On the far side of the sky, Earth glows faintly, familiar, distant, unreachable. The place that shaped their biology is no longer within reach. The place they inhabit must be built, moment by moment. We arrive now at the deepest paradox of Martian settlement, the paradox of purpose. Mars is uninhabitable, yet we choose to live there, not because it is easy, but because it clarifies what survival requires. Mars strips life to its essentials: air, water, pressure, heat, knowledge. By removing everything unnecessary, the planet reveals what is fundamental. This knowledge does not weaken humanity. It sharpens our understanding of life itself. A micro-story ties the paradox together. During a quiet night, a crew member checks the habitat's sensors. All readings are normal: pressure stable, oxygen steady, water levels balanced. Outside, the temperature is far below freezing. The air is thin enough to dissipate breath instantly. The crew member realizes that every condition inside exists because humans created it, not because the planet offers it. The paradox becomes personal. Living on Mars means living in a world shaped entirely by human understanding, surrounded by a world shaped entirely by natural indifference. Two opposing sentences settle the tension. Mars gives us nothing we need. Mars gives us every question worth asking, and the subphase ends on a quiet line. Mars remains uninhabitable, yet becomes the clearest place to understand what life truly requires. Knowledge becomes the stabilizing force in a world where distance and environment combine to create constant tension. On Mars, understanding is not optional. It is the architecture beneath every breath, every decision, every cultivated plant, every repaired machine. Distance from Earth does not simply increase the need for knowledge, it transforms knowledge into the basis of autonomy. We begin with the idea of operational independence. Mars settlers must make decisions without waiting for Earth. This requires not only training, but systems designed to surface information clearly. Pressure trends, temperature curves, energy projections, water reserves. Each dataset becomes a tool for survival. Knowledge shifts from passive reference to active infrastructure. A visual cue anchors this. Inside a habitat control room, a large display shows a simplified representation of the entire settlement. Lines indicate airflow, colours indicate temperature zones, icons mark power routing. Nothing about this environment is intuitive. Everything is visible because it must be understood deliberately. Next, knowledge expands into fault anticipation. On Earth, systems fail and repair teams respond. On Mars, repairs must occur before failures escalate. Predictive algorithms monitor mechanical vibration, chemical balance, suit integrity, and power distribution. These systems alert crews not to problems, but to precursors of problems. Mars forces knowledge forward in time. A reflection fits. Living on Mars means knowing not only how things work, but how they are about to stop working. This anticipation connects to resource literacy, another essential category of understanding. Water is finite. Soil requires treatment. Energy must be budgeted. Oxygen must be continually generated. Waste is never discarded. The settlers become intimately aware of every resource's origin, transformation, and endpoint. This awareness is not philosophical, it is operational clarity. Two opposing sentences illustrate the shift. Earth hides abundance, Mars exposes requirements. A micro-thought experiment deepens the idea. Imagine a crew member using a cup of water. Before drinking, they know where the water was sourced. Ancient ice melted in a processing unit. After drinking, they know where it will go. Interfiltration systems, separated into clean water and nutrients, eventually returning to circulation. Knowledge turns consumption into continuity. Now consider scientific literacy, which deepens on Mars because every observation carries meaning. The angle of shadows reveals dust density. The stiffness of a suit joint hints at temperature changes. The sound of a pump indicates internal pressure fluctuations. Mars demands attentiveness to signals that would seem trivial on Earth. A visual cue clarifies the environment. A crew member walks through a greenhouse. Their steps are quiet on the padded floor. Above them, lights shift colour as sensors detect plant growth stages. The air is warm and moist. Every sensation, the smell of soil, the hum of fans, communicates system status. Knowledge blends with perception. Another layer is planetary understanding, essential for exploration. Mars's terrain has hazards invisible to untrained eyes. Soft dust pockets, hidden slopes, radiation hotspots. Rovers map these systematically. Humans learn to read the land through topographical data, not instinct. Mars replaces familiarity with measurement. A reflection arises. On Earth, we trust our senses. On Mars, we trust our instruments. Then comes psychological knowledge, equally crucial. Distance from Earth introduces stress that cannot be solved with engineering alone. Settlers need an understanding of isolation, circadian rhythms, group dynamics, and the mental effects of confined spaces. Knowledge about the mind becomes as vital as knowledge about air quality or pressure systems. A micro-story highlights this. Late at night, a crew member sits near a window. Outside, the land lies silent. Earth appears as a tiny point of light. The crew member reviews messages sent hours earlier, knowing replies will take just as long. Their calm is supported by routines informed by psychology. Regular group check-ins, structured days, planned solitude. Knowledge does not erase isolation, but it helps integrate it. The next category is procedural knowledge, the set of routines that keep life support running. Every system has a maintenance schedule, measured not in weeks but in hours or days. Filters must be checked, surfaces cleaned, sensors calibrated. These procedures become part of daily life, as familiar as cooking or exercise. Settlers live not around these tasks, but through them. Two opposing sentences shape this. Earth life flows within an environment. Mars life flows within procedures. Another key dimension is collaborative knowledge. On Mars, every person must understand enough about many systems to assist with repairs, emergencies, and maintenance. Specialization still exists, but redundancy in skills mirrors redundancy in machinery. A botanist must know how to fix a valve. An engineer must know how to manage nutrient cycles. Knowledge spreads horizontally, not vertically. A visual cue reinforces this. In a quiet workshop, 3 crew members stand around a disassembled air filter. One is an engineer, one a biologist, one a medical officer. All understand the basic function, all can help reassemble it. Their roles blend because the planet demands it. We approach the final layer, knowledge as identity. On Earth, identity often comes from culture, profession, or environment. On Mars, identity forms around competence, the shared ability to maintain life where nature does not. Settlers will see themselves not as residents of a harsh world, but as maintainers of a carefully constructed one. Their environment is not found, it is sustained. A reflection fits quietly. On Mars, knowledge is not an advantage. It is the atmosphere we breathe. As we conclude the subphase, a final visual cue settles into place. Night has fallen again. The land cools instantly, but inside the habitat, lights glow with consistent warmth. Plants continue their growth cycles. Instruments continue their monitoring. Humans rest while knowledge works on their behalf, and the subphase resolves with a single calm line. On Mars, survival becomes possible only when knowledge becomes continuous. The invisible environment that keeps life alive. Mars is uninhabitable, yet one anchor fact drives continued planning for long-term settlement. Mars has a stable day-night cycle that closely matches Earth's, even though nothing else about the planet supports human life. This single alignment, a day just slightly longer than 24 hours, shapes circadian rhythms, agricultural planning, energy cycles, and psychological stability. It is a familiar rhythm inside an alien world. This rhythm becomes the first reliable structure humans can use. A visual cue grounds the idea. Light slowly spreads across a Martian plain. Shadows shift in a way that feels natural to human perception. The sun rises with a familiar pace, even if the sky is tinted red. As daylight strengthens, solar panels angle themselves toward the light. Inside a habitat, crew members begin their routines. The length of the day matches their expectations. Everything else does not. This creates an interesting anchor. Mars is uninhabitable in nearly every physical category, yet provides a temporal structure so similar to Earth's that humans can synchronize life support systems, work shifts, and internal clocks without major adaptation. A reflection fits here. Life does not require identical conditions to Earth, but it does need patterns that bodies can trust. This alignment serves as a foundation for settlement design. Light cycles coordinate greenhouse operations. Energy consumption follows predictable daily curves. Humans sleep roughly when night arrives, and work when light returns. The planet dictates a rhythm that does not need to be manufactured. In contrast, almost everything else must be built artificially. Air pressure, water cycles, nutrient systems, radiation shielding, and temperature control. This contrast becomes clearer when paired with another anchor fact. While the Martian day is stable, the environment within that day is not. Temperatures swing dramatically. Radiation fluctuates with solar activity. Wind occasionally lifts dust into the sky, dimming the light. The day feels familiar, but the conditions within it remain hostile. A micro-story illustrates this duality. A crew member steps into an airlock to begin a morning EVA. Inside the habitat, the clock reads a time that feels natural. Outside, the sky glows with a soft orange. The sun appears small but steady. Yet, the moment the airlock depressurizes, the body confronts the truth. The air is unbreathable, the temperature freezing, the suit essential. The rhythm is familiar. The world is not. Another key anchor. Mars has seasons, long, cold, and subtle, but real, driven by the planet's axial tilt. These seasons influence sunlight, atmospheric density, and dust storm frequency. They serve as long-term markers. Settlements can plan crop cycles and energy reserves around these patterns. When dust storms are more likely, habitats prepare for reduced sunlight. When temperatures shift, thermal systems adapt. A visual cue deepens the sense of scale. During the Martian winter, frost forms on the edges of rocks. The ground gleams faintly in the low sun. Winds move slowly, pushing fine grains of ice. Nothing grows, nothing melts. The planet changes, but only slightly, and over long stretches of time. This stability in long-term cycles becomes a hidden advantage. On Earth, weather changes rapidly. Storms form and dissipate within hours. Mars lacks this turbulence. Its atmosphere is thin, its clouds rare, its weather slow. Settlers can plan not only days ahead, but weeks and months. Predictability becomes a form of safety. Two opposing sentences reveal the dual nature of this anchor. Mars changes slowly, but dangerously. Earth changes quickly, but safely. The next anchor fact is geological. Mars's surface preserves ancient features with extraordinary clarity. Volcanoes frozen in time, riverbeds from billions of years ago, sediment layers untouched by erosion. Settlements can be built near cliffs, caves, or lava tubes that have remained structurally sound for eons. The ground does not shift unexpectedly. A reflection fits. Mars is uninhabitable, but it is stable. Stable in ways Earth is not. This stability allows engineers to build long-lasting structures. Foundations do not need to adapt to earthquakes or rapid erosion. Tunnels carved into lava tubes remain steady. Subsurface habitats stay intact for long periods. The ground becomes a partner, even as the atmosphere remains an adversary. A micro-thought experiment illustrates this. Imagine building a habitat inside a small lava tube. The interior is sheltered from radiation, insulated from temperature swings, and protected from dust storms. The structure can anchor to rock that has not moved for millions of years. Outside, the wind blows thin dust. Inside, life persists in a chamber carved by volcanic forces long before humans existed. Another anchor fact emerges. Mars offers resources in predictable locations. Water ice appears at high latitudes and beneath certain plains. Certain minerals consistently cluster in specific formations. This predictability reduces exploratory uncertainty. Robots and rovers already map deposits with high precision. A visual cue reinforces the point. In the soft afternoon light, a rover drills into a patch of soil predicted to contain ice. Vapor rises as the drill warms the sample. The prediction was correct. The knowledge becomes a resource, and through these anchors, a deeper idea emerges. Mars is uninhabitable, but it is reliable. Its dangers are constant, its climate slow, its geology stable. These traits allow human planning to take root. As this subphase closes, the anchor fact resolves gently. Mars offers no natural habitability, yet provides a stable rhythm and terrain on which human-designed life can grow. To understand why Mars, despite being uninhabitable, can still host long-term human presence, we need to examine the mechanisms that convert the planet's stability into usable systems. These mechanisms do not eliminate the dangers. Instead, they transform steady patterns, day length, terrain consistency, slow climate change, into operational advantages. The first mechanism emerges from the Martian day cycle. Because a sol is only slightly longer than an Earth day, life support systems can operate on familiar rhythms. Temperature control runs on daily curves. Greenhouses adjust light intensity in predictable 24-hour cycles. Human circadian rhythms align naturally, reducing stress and improving sleep. This simple alignment reduces the cognitive strain of living on a foreign world. A visual cue grounds this. As the Martian sun rises, soft, orange light enters the greenhouse through filtered panels. Inside, lights dim slightly to transition from artificial night to real dawn. Plants experience a rhythm that mirrors Earth even though the world outside remains cold and airless. The next mechanism comes from seasonal patterning. Mars's long, slow seasons allow settlements to predict energy availability months in advance. During winter, solar power drops, so reactors or stored energy play larger roles. During summer, sunlight increases, allowing for higher agricultural output. Nothing about the climate is warm or comfortable, but its slow pace permits planning that Earth's turbulent weather would disrupt. A reflection fits here. On Mars, stability does not mean safety. It means predictability. Now we move to thermal management, a mechanism shaped by daily and seasonal temperature swings. Mars cools rapidly at night, which would freeze equipment if not protected. Habitats use multi-layer insulation, internal heat exchangers, and thermal mass to smooth these swings. Waste heat from power systems is captured and reused to warm infrastructure. Unlike Earth, where heat dissipates gently into the environment, Martian systems must trap and recycle every joule. A micro-thought experiment clarifies the design. Imagine a habitat at dusk. Outside, the temperature drops quickly. Inside, a network of pipes directs warm air through walls and floors. Sensors measure the rate of cooling and shift energy from storage units to heaters. Nothing is wasted. Every movement of heat is deliberate, monitored, controlled. Another key mechanism arises from terrain stability. Because Mars lacks plate tectonics, earthquakes are rare and minor. Settlements can anchor to rock formations that have not shifted for millions of years. This stability allows for deep foundations, long-term underground construction, and the use of natural lava tubes as protected habitats. Engineers can predict structural loads accurately because the ground beneath them barely changes. A visual cue reinforces this. In dim morning light, the entrance to a lava tube appears as a dark ellipse at the base of an ancient volcanic mound. A small rover sits near the opening, its headlights illuminating rough stone that has been untouched since long before life on Earth became complex. Now consider resource extraction, a mechanism built on geological predictability. Water ice occurs in specific latitudes and under certain plains. Minerals appear in characteristic formations. Settlement designers place outposts where drilling is feasible, not because the environment is friendly, but because the map of resources is reliable. Another visual. A robotic auger lowers into the ground. As it drills, instruments confirm the presence of ice at the expected depth. Vapor rises from the heated chamber, captured and condensed into liquid water. The mechanism works because the subsurface behaves exactly as predicted. Next is radiation mitigation, tied closely to Mars's steady, unchanging sky. Unlike Earth, radiation exposure does not fluctuate rapidly. By measuring solar cycles and cosmic ray levels, habitats calculate safe exposure times for outside work. Dosage accumulates slowly and predictably. Shielding materials can be refined based on long-term measurements rather than short-term fluctuations. A reflection arises. Mars does not warn us, but it does not surprise us either. We then examine pressure management, another mechanism dependent on stability. Because external pressure is extremely low but constant, habitat shells are built with uniform outward force in mind. Engineers design them as inflated structures where internal pressure keeps walls tense and rigid. This allows for large domes, tunnels, and modular expansion. The vacuum outside is deadly but consistent. making structural calculations straightforward. A micro-story illustrates it. Inside a construction dome, workers assemble a new greenhouse module. The frame looks delicate until pressure is added. As air fills the structure, the walls stiffen, stabilizing into a strong, self-supporting bubble. The danger outside becomes the support mechanism inside. Now we introduce dust management, an often overlooked mechanism shaped by Mars's slow weather. Dust moves across the planet in fine layers. While storms can last weeks, winds are generally predictable. Settlements use electrostatic panels, rotating brushes, and angled surfaces to keep solar arrays clear. Sensors detect dust accumulation and activate cleaning systems without human intervention. A visual cue enhances the moment. A long arm sweeps across a solar panel at dawn, brushing away a thin layer of red dust. The sun rises, light reflects, and battery levels begin to climb. The next mechanism is transport coordination. Because the terrain changes slowly, navigation maps remain valid for long periods. Autonomous rovers rely on terrain models that rarely require updates. Routes between settlements, resource sites, and research areas remain reliable. This reduces risk and conserves energy. A reflection fits neatly. Mars challenges life, but not navigation. Finally, we reach the mechanism of temporal integration. Mars's slow climate, steady geology, and predictable patterns allow long-term planning. Multi-year agricultural schedules, material production cycles, and energy budgeting. Humans can build decades-long strategies because the planet itself changes very little over such spans. Two opposing sentences bring the mechanism into focus. Mars forces constant protection. Mars allows long-term planning. As this subphase closes, the mechanisms converge into a single understanding. Mars remains uninhabitable, but its slow rhythms and stable terrain give us the predictable structure needed to engineer life within it. The paradox at the center of Mars's stability is simple. A planet that barely changes creates both opportunity and danger for human life. The same slow rhythms that support long-term planning also trap settlers inside conditions that never improve. Stability becomes both a foundation and a limitation. We begin with the first layer. Mars changes so slowly that buildings, tunnels, and infrastructure remain undisturbed for generations. This makes life predictable, but predictability does not mean progress. Mars will not warm on its own. Its atmosphere will not thicken. Its radiation will not decrease. The environment settlers encounter on day one will be the same after 50 years. Time on Mars brings learning, not relief. A visual cue captures this. A small settlement sits at the base of an ancient ridge. 10 years have passed. The ridge looks identical. The dust shifts, but the rock does not move. Nothing grows, nothing erodes significantly. The land remains frozen in its own history. This creates a paradox of stillness. Mars offers long-term stability, but no natural evolution toward habitability. A reflection follows. On Earth, life adapts because the world changes. On Mars, life must adapt because the world does not. The second layer of paradox comes from the reliable day-night cycle. Settlers benefit from circadian familiarity. Plants grow in predictable rhythms. Energy demand follows daily patterns. But within this stability lies a second contradiction. Each day brings both life-supporting structure and life-threatening exposure. Daylight warms the land slightly, but does not make it safe. Night arrives as a rapid drop to dangerous temperatures. Two opposing sentences sharpen the tension. The Martian day feels familiar. The Martian environment feels alien every minute. A micro-story illustrates this conflict. A crew member wakes at sunrise, feeling the natural cue of light through a filtered window. They begin their morning routine, grounded by the rhythm of time. An hour later, they suit up to inspect equipment outside. The familiar rhythm vanishes instantly as they step into a world where breathing requires machinery, and a single tear in a glove could be fatal. The day is human-friendly, the air is not. Next comes the paradox of geological stability. Mars's surface preserves ancient features, untouched by erosion or tectonics. Engineers appreciate this reliability, but for scientists, it reveals a tension. The land is filled with records of water and climate that no longer exist. Ancient riverbeds promise answers, but remind us constantly that the planet abandoned habitability long ago. A visual cue deepens the feeling. A rover scans a canyon carved by flowing water billions of years before humans evolved. The canyon is pristine, its shape is sharp, nothing has blurred its edges. It holds memories that the planet will never revisit. This leads to another paradox. Mars reveals life's past possibilities while demonstrating life's present impossibilities. A reflection emerges. It is a world that can show us what life needs, but cannot give it. The fourth layer comes from the slow seasonal cycles. Mars's seasons allow long-term planning, but create long-term vulnerability. When a dust storm season approaches, settlers can prepare, but they cannot escape it. The storms may block sunlight for months, crops may slow, power systems may strain. Stability gives warning, but not protection. A micro-thought experiment clarifies this. Imagine knowing a storm will last 6 weeks. Energy reserves are full, systems are prepared. Yet sunlight fades, and every day becomes a calculation. How much power to spend? How much to save? How much redundancy to use? Stability provides foresight, but foresight cannot improve the environment. This paradox becomes clear. Predictability reduces surprise, not danger. The next layer concerns human perception. Mars's stability is comforting at first. The horizon remains unchanged. The days follow a steady rhythm. But over time, the unchanging environment becomes a psychological weight. The landscape is vast, but nothing within it responds. No seasons of colour, no rain, no sound of water, no movement of life. A reflective line fits. Mars offers consistency, but not connection. A visual cue strengthens this emotional paradox. A crew member stands near a window. Beyond the glass, the same plane stretches toward the same ridge, under the same pale light. Weeks pass, months pass, the scene never changes. The stillness becomes a reminder that they live on a world without biological cycles. Now we reach the paradox of autonomy. Mars forces humans to become more independent, capable, and self-sufficient. But this autonomy emerges only because the environment leaves no room for error. Settlers gain freedom through discipline. They gain capability through constraint. Two opposing sentences define it. Mars makes humans more capable. Mars gives humans fewer chances to fail. The final layer is the paradox of ambition. Humanity moves to Mars seeking expansion, exploration, and new horizons. But the act of living there requires retreat into tunnels, domes, and carefully controlled interiors. We expand our presence in the solar system, while contracting our physical world to small, curated environments. A micro-story anchors this final tension. A child born on Mars grows up inside a habitat with controlled air, filtered light, and floors warmed by recycled heat. They learn to walk in reduced gravity. They learn to play inside safe rooms. Outside, the world is immense but inaccessible without layers of protection. Expansion creates confinement. As this subphase nears its close, the paradox resolves into a single insight. Mars gives humans a future beyond Earth, but only by revealing every limit of human biology and every requirement of human engineering. It challenges us by being stable where we are dynamic, empty where we expect life, predictable where we expect change, and the subphase settles on a quiet line. Mars is uninhabitable, yet its unchanging nature becomes the framework in which human life can endure. Knowledge is what transforms Mars's slow, unchanging character into a usable foundation for human life. Stability by itself does not create safety. It creates the space in which understanding can take root. On a world that will not evolve to meet human needs, knowledge becomes the evolving element, the growing system that adapts in place of nature. We begin with the core concept, predictive operations. Because Mars changes slowly, knowledge about its cycles can drive long-term planning. Engineers model temperature swings, solar power curves, and seasonal dust patterns years in advance. This knowledge guides resource storage, crop scheduling, and habitat insulation upgrades. The planet does not offer comfort, but it offers data, and data becomes the first layer of reliable survival. A visual cue anchors this. Inside a control hub, a long graph stretches across a screen. It shows predicted sunlight for the next Martian year. Small rises and dips, no sudden spikes. Beneath it, a second graph displays expected power production. Crew members adjust planning not by reacting, but by aligning with patterns that barely shift. Now knowledge extends into environmental mapping. Rovers, drones, and orbiters collect detailed data about soil composition, radiation levels, ice deposits, and geological fractures. On Earth, such data supports exploration. On Mars, it determines where humans can safely build, drill, and expand. Knowledge replaces instinct and walks ahead of every decision. A reflection fits quietly. Where Earth gives intuition, Mars demands information. This leads to structural understanding, the knowledge of how habitats interact with a near-vacuum environment. Engineers model every connection point, every stress curve, every thermal gradient. They predict how materials expand and contract with temperature cycles, how tunnels behave over decades, how shields degrade under radiation. This knowledge allows habitats to last long enough for generations to live within them. A visual cue reinforces this stability. In a dim workshop, an engineer runs a gloved hand along a curved wall. Behind it, sensors embedded in the structure send tiny pulses of data about tension, temperature, and micro vibrations. The wall is not a barrier, it is a monitored ecosystem of material. Knowledge deepens into ecological engineering, the design of closed-loop systems that mimic Earth's cycles in miniature. Every element, air, water, nutrients, microbes, is measured, balanced, and recycled. There is no wilderness on Mars, no fallback ecosystem. Instead, knowledge builds an engineered nature. Plants grow because sensors adjust moisture. Microbes process waste because conditions are monitored. Water cycles through filters instead of clouds. Two opposing sentences capture the shift. Nature guides life on Earth. Knowledge guides life on Mars. The next dimension is behavioral knowledge, essential for psychological stability. On Mars, isolation is predictable and monotony is unavoidable. Researchers study long-duration missions on Earth, Antarctic stations, undersea labs, simulated Martian habitats, to understand how teams maintain well-being. Schedules, shared tasks, private time, and communication protocols all emerge from this accumulated understanding. A micro-story illustrates it. In the evening, crew members gather in a shared module. They eat together, discuss the day, and check in on one another. These routines are not casual. They are grounded in research showing that group cohesion reduces stress during long isolation. Knowledge shapes even the simplest moments. Next comes biological knowledge, which becomes richer the longer humans live in reduced gravity. Physicians monitor bone density, muscle mass, cardiovascular changes and sleep patterns. Over time, researchers gain a clearer understanding of how the human body adapts to a world with weaker gravity and higher radiation. This knowledge guides exercise regimens, nutrition, and medical protocols. Another reflection emerges. Mars does not respond to our biology. Our biology must respond to Mars, through knowledge. Now consider operational literacy, a key form of knowledge that every settler must hold. Because systems are interconnected, understanding one mechanism, water recycling, air processing, thermal control, often requires understanding several others. The crew becomes multi-skilled by necessity. Knowledge spreads horizontally across disciplines, creating resilient teams. A visual cue clarifies it. 3 crew members lean over a maintenance table. One is a botanist, one an engineer, one a geologist. They review sensor data from a failing pump. Each understands enough of the system to help diagnose the issue. Their roles blend seamlessly because Mars requires overlapping expertise. Knowledge expands further into material science. Martian regolith can be transformed into building material, radiation shielding, and even composites for manufacturing. Scientists study particle size, mineral composition, and chemical behavior under heat. This knowledge allows settlements to grow without expanding dependence on Earth. A micro-thought experiment shows the transformation. Imagine heating regolith inside a furnace. The particles fuse into a ceramic-like block. Once cooled, this block becomes part of a new tunnel wall. The wall did not come from Earth. It came from understanding how Martian soil behaves under controlled processes. The next layer is planetary knowledge, built from scanning Mars at every scale, from orbit to surface. These maps show where dust storms originate, where ancient water once flowed, where radiation levels are lowest. They guide exploration and construction for decades. Mars cannot be made hospitable, but it can be made readable, and reading a planet clearly is the first act of inhabiting it responsibly. Now we reach the deepest form of knowledge, adaptive understanding. the ability to change systems based on new insights rather than simply following predefined protocols. On Mars, every anomaly teaches something: how dust coats surfaces, how ice sublimates, how pressure systems behave after years of use. Knowledge grows because the planet remains constant. Its stability allows understanding to accumulate reliably. Two opposing sentences settle this idea. Mars will not improve for us, but we will improve for Mars. A final visual cue closes the subphase. Night falls again. Outside, the air is thin and silent. Inside, plants give off faint oxygen. Water drips through a recycler. Engineers review sensor logs. Nothing outside has changed. Everything inside continues through knowledge, and the subphase resolves with a quiet truth. On Mars, knowledge becomes the enduring environment, the steady atmosphere within a world that offers none. The next anchor fact begins with a quiet but profound reality. Mars cannot support human reproduction naturally, yet long-term settlement requires the possibility of raising children in an environment that does not sustain life. This is one of the sharpest lines between exploration and habitation. Visiting Mars is a technological challenge. Living on Mars for generations is a biological and societal one. This anchor sets a new tone. It shifts attention from engineering to humanity. A visual cue opens the scene. Inside a habitat, artificial light moves across a shared space, designed for exercise, meals, and conversation. The room feels familiar but slightly altered. Lower gravity, filtered air, mechanical hums behind walls. Everything is carefully structured, yet the space remains small. Outside, a vast, empty plain stretches to a quiet horizon. This contrast reveals the anchor. Mars can host settlements, but not societies. Not yet. We begin with the biological facts. Humans evolved under Earth's gravity, radiation shielding, atmospheric pressure, and magnetic protection. These conditions shape gestation, bone development, immune function, and early childhood growth. Mars provides none of them. Reduced gravity changes how fluids move inside the body. Radiation affects genetic material. Pressure differences shape cellular processes. Even light cycles, though similar in length, have different intensities. A reflection fits here. Our bodies are stories written by Earth's physics. Now consider the next layer of the anchor fact. Children born on Mars would experience a world fundamentally incompatible with unassisted human life. Every moment of their existence would depend on enclosed spaces, engineered systems, and artificial climates. They would never breathe outside air, feel unfiltered sunlight, or stand under an open sky without protection. Their entire sense of the world would form inside controlled environments. A microstory illustrates this. A child stands at a thick window looking out at the landscape. They know the world outside is beautiful and dangerous. They play in rooms with soft walls, walk on floors heated by recycled energy, and sleep under LEDs tuned to mimic Earth's dawn. For them, Earth is not home. It is a distant concept seen only in images and heard in stories. This leads to a deeper anchor. Mars can support human presence but not human development, without constant adaptation and oversight. Yet another layer emerges when we consider social structure. Communities develop instinctively on Earth because resources are abundant and environments support growth automatically. On Mars, social life must be designed with intent, shared routines, group cohesion, conflict management, psychological support. Every community dynamic takes place inside small, pressurized spaces where privacy is minimal and cooperation is essential. A visual cue grounds this. In the evening, a group of settlers gathers in a shared dome. The air is warm, lights dim gradually, and the sound of circulating fans forms a soft background logo. Conversations are calm but deliberate. Everyone understands that the social fabric here is as critical as the engineering. Now the anchor fact sharpens. Mars does not allow accidental survival. Nothing can be taken for granted. Not air, water, heat, or community cohesion. Even education changes. Children on Mars would learn science not as distant abstraction, but as daily context. They would understand pressure differentials before learning geography. They would learn about oxygen recycling before learning about forests. Their earliest lessons would be about why the world outside cannot be entered without a suit. A reflection emerges naturally. Mars turns survival into curriculum. This leads to one of the most profound anchoring truths. Generational life on Mars requires redefining what normal means. Normal becomes engineered, predictable indoor. Earth-like conditions are not experiences, they are settings. Humanity expands into a new world, but carries Earth inside pressurized walls. A visual cue deepens the image. A small garden grows under bright artificial lights. Children touch the leaves gently. They smell the soil, a mix of processed regolith and compost. They learn that plants survive here only because people create the right environment. They understand instinctively that nature is not outside, but inside. This brings us to the core of the anchor fact. Mars is uninhabitable for natural human life, but it becomes habitable for designed human life. Life supported by layers of knowledge, engineering, and social adaptation. The planet itself contributes almost nothing directly to survival. Everything depends on systems we build and maintain. Two opposing sentences capture the tension. Mars can host our structures. Mars cannot host our biology unassisted. The anchor deepens further when we consider belonging. Generations raised on Mars may see Earth as foreign. Their bodies would adapt to lower gravity. Their sense of normal would be shaped by enclosed spaces. Their concept of outside would differ entirely from Earth-born humans. They may become physically unable to return to Earth's stronger gravity. A micro-thought experiment makes this tangible. Imagine a teenager born on Mars stepping into a ship bound for Earth. They arrive after months of travel. Gravity pulls on their bones and muscles with overwhelming force. Their heart works harder. Their balance shifts. Earth is beautiful. Oceans, forests, open skies. But their body struggles. Mars, dangerous and barren, feels physically familiar. Home becomes defined not by beauty, but by biology. And here, the anchor fact lands with clarity. Mars is uninhabitable. Yet, it may shape a new branch of human experience. One that grows inside engineered environments, not natural ecosystems. As we approach the end of this subphase, the anchor settles into a quiet, stable line. Mars cannot nurture human life by nature, yet it may become the place where human life evolves by design. To understand how life could continue across generations on a world that cannot support human biology naturally, we must examine the mechanisms that protect, guide, and shape development in an uninhabitable environment. These mechanisms are not only technological, they are biological, medical, psychological, and social. Layers of support that replace what Earth's environment provides effortlessly. We begin with the mechanism of radiation protection, a foundational requirement for human reproduction and growth. Mars receives a constant stream of high-energy particles because its atmosphere is thin and its magnetic field is weak. For children, whose cells divide rapidly, radiation is especially dangerous. Shielding becomes the first protective mechanism. Habitats for families must be placed underground or inside thick-walled structures, using regolith, water tanks, or composite materials to absorb radiation. A visual cue grounds this. Inside a softly lit habitat, an internal corridor curves beneath several meters of soil. Sensors on the walls show near-zero radiation levels. Outside, the signal readings spike. The soil does not simply cover the habitat, it becomes the planet's substitute for the magnetic field Mars lost long ago. The next mechanism involves gravity compensation. Reduced gravity affects bone development, muscle growth, fluid distribution, and vestibular balance. For adults, exercise routines counteract these effects. For children, whose bodies develop rapidly, compensation must be embedded into the environment. Rotating rooms, artificial gravity platforms, and resistance-based play areas create intermittent periods of higher gravitational load. These mechanisms help bones grow dense enough and muscles strong enough to support healthy development. A micro-thought experiment makes this tangible. A child runs in a circular play ring where the floor subtly curves. As the ring spins slowly, the child feels heavier for a moment. They laugh, not realizing that the increased load strengthens their bones. What feels like play is actually a physiological mechanism engineered into daily life. The next layer is atmospheric engineering. For adults, stable pressure and oxygen levels maintain health. For developing bodies, these conditions must be even more precise. Air inside family habitats is kept at consistent pressure, humidity, and oxygen concentration. Sensors track contaminants, particulates, and carbon dioxide levels continuously. Infants breathe extremely clean air because their lungs are more sensitive to pressure fluctuations. A reflection fits naturally. On Earth, the atmosphere raises us. On Mars, we must raise the atmosphere ourselves. Now we move to nutritional mechanisms. Martian agriculture will rely on controlled environments. Plants grow in purified soil made from regolith, supplemented with organic matter. Light is tuned to optimize micronutrient density. Water cycles through multi-stage filtration systems. Nutritionists design diets that compensate for low gravity, higher radiation exposure, and limited food variety. Children's diets are adjusted in real time according to growth metrics captured by medical sensors. A visual cue deepens the scene. In a greenhouse, rows of leafy plants sway under pink-white LED arrays. A small sensor clipped to a leaf records moisture levels. The entire room is a mechanism. The soil, the air, the light, the water, all calibrated to produce food for a world that provides none naturally. Next comes the mechanism of genetic monitoring. Not for modification, but for protection. Families undergo regular screenings to track radiation-induced mutations. Mars does not change quickly, but radiation exposure accumulates over a lifetime. Monitoring systems identify issues early, so medical teams can intervene before small problems become large ones. These mechanisms extend the reach of preventive care into realms Mars threatens directly. A micro-story illustrates this. A doctor reviews a child's quarterly health scan. Charts show bone density, muscle mass, radiation markers, sleep patterns, and nutrient absorption. Each trend is compared against Earth-based developmental curves. The doctor adjusts exercise routines and diet plans. The mechanisms work silently, shaping healthy growth in an environment that does not support it. Now we explore spatial mechanisms, the architecture of movement and exploration for developing humans. Children cannot walk outside freely. Their outside is interior. Settlements include multi-room walking loops, climbing structures, and open spaces shaped like small parks with artificial grass, soft flooring, and controlled lighting. These spaces mimic Earth environments, not for nostalgia, but for motor development and mental resilience. A reflective line fits gently. Mars forces us to create places where movement is safe, even when the world outside is not. Communication becomes another essential mechanism. Because Mars is distant, real-time conversations with Earth are impossible. To counter loneliness, habitats integrate asynchronous communication systems, video diaries, recorded messages, and shared educational streams that help children feel linked to a larger human story. This mechanism reduces the psychological weight of living in isolation. A visual cue reinforces it. A child sits with a tablet watching a delayed message from grandparents on Earth. The signal took minutes to arrive, but the laughter feels immediate. Distance softens slightly through intentional design. The next mechanism is education, structured around environment. Children learn about pressure safety, suit protocols, and habitat maintenance from an early age. These lessons are not abstract. They are woven into games and daily tasks. Mars becomes the practical foundation for learning. Cause and effect, system feedback, environmental science, and survival logic. A micro-thought experiment brings this into focus. A group of children practices a drill, sealing a mock airlock, checking indicator lights, and verifying pressure readings. They treat it like play, but the mechanism behind the activity ensures instinctive knowledge of emergency responses. Now we reach one of the most delicate mechanisms: social stability in confined environments. Mars settlements depend on cooperation. Disputes cannot escalate. Psychological strain cannot be ignored. Mechanisms for group cohesion, shared meals, scheduled quiet hours, communal work blocks, rotating responsibilities, keep communities resilient. Children absorb these rhythms as part of normal life. Two opposing sentences clarify the idea. Mars restricts space. Community expands within it. The final mechanism is identity formation, shaped indirectly by every system. Children grow up seeing Earth as distant and Mars as normal. Their sense of belonging forms around the habitat, not the horizon. For them, the mechanisms of survival become the environment itself, an engineered world where life persists through design. A last visual cue closes the subphase. Night settles outside the habitat. Temperature drops instantly. Inside, the light warms to a soft glow. A group of children plays in a low-gravity room, bouncing gently as the floor responds with controlled resistance. Everything around them, the air they breathe, the gravity they feel, the walls that protect them, is a mechanism working continuously, and the subphase resolves with a quiet insight. On Mars, human development depends on systems that replace the environment itself, turning survival into a carefully engineered continuity. The paradox of raising new generations on Mars begins with a difficult truth. A world that cannot support human life naturally may become the first place where humanity transforms itself intentionally. Mars resists biology at every scale, yet invites us to imagine futures where human adaptation is guided, measured, and deliberate. This tension between resistance and possibility shapes one of the deepest paradoxes of interplanetary life. We begin with the first layer of contradiction. Mars cannot nurture pregnancy or childhood under natural conditions. Reduced gravity alters developmental pathways, radiation threatens cellular growth, isolation affects psychology. Yet these challenges push us toward more advanced medical monitoring, better understanding of human physiology, and deeper insight into how life evolves under different planetary conditions. Two opposing sentences frame the tension. Mars endangers human development. Mars reveals the boundaries of human development. A visual cue deepens the paradox. In a quiet medical bay, a screen displays growth metrics for a child. Each line traces bone density, muscle formation, lung capacity. The curves differ slightly from Earth norms, not dangerously, but distinctly. The child is healthy, yet evolving in a world their ancestors never experienced. This leads to a reflection. Mars does not change quickly enough for nature to adapt, so humans must adapt through knowledge. The next layer of paradox arises from safety and confinement. Children must grow within enclosed, engineered spaces because the outside environment is lethal, yet these artificial interiors may become more stable and predictable than many environments on Earth. The child's world is small but controlled, limited but secure. Mars shrinks the horizon while increasing reliability. A microstory illustrates this. The child practices walking in a soft-walled play area. The floor adjusts to provide resistance. Lights shift gradually to mimic Earth-like dawn. Air composition is perfect. Outside, dust moves silently across a barren plain. Inside, conditions are ideal for development. The contradiction is clear. The least hospitable world becomes a carefully crafted cradle. Another paradox forms around identity. Children raised on Mars may feel at home in a place that cannot sustain them without technology. Their bodies may grow accustomed to low gravity. Their instincts may form around enclosed habitats. Earth, with its open skies, forests, oceans, and variable weather, may feel overwhelming. They belong to a world that cannot support their biology outside controlled boundaries. Two quiet sentences sharpen the tension. Mars cannot host life naturally, but life raised there may not feel natural anywhere else. A reflection follows. Mars becomes home not because it is welcoming, but because experience shapes belonging. Next, we confront the paradox of fragility and resilience. Mars makes life fragile. A single system failure endangers survival. Yet the constant awareness of this fragility may produce unprecedented resilience. Children grow up understanding cause and effect, system dependence, emergency routines, and cooperative living. They learn that survival is shared, not individual. Fragility fosters strength. A visual cue reinforces the idea. A group of children rehearses an emergency drill calmly. They seal mock airlocks, check indicator lights, and confirm pressure readings. Their actions are careful but unafraid. They grow strong within the constraints of an unforgiving world. Another paradox emerges from communication. Children on Mars will know Earth through delayed messages, images, and stories. Earth becomes both real and unreachable, familiar yet remote. Mars gives them technological connection without physical presence, creating a form of relationship shaped not by distance alone, but by time. A reflection fits here. Children on Mars will grow up connected to Earth, but not defined by it. The next layer concerns evolution and stasis. Mars forces human biology into a stable but altered pattern. If generations grow up in reduced gravity, their bodies may adapt, longer limbs, different bone density, modified heart function. Yet the environment itself does not change. Biological adaptation may occur within a planetary setting that remains static. Evolution meets stillness. This produces a paradox of future identity. Humanity may diversify not because environments differ, but because technology makes new environments viable. A micro-thought experiment pushes this forward. Imagine a few generations later, a child born on Mars takes their first steps in low gravity. Their bones have grown in patterns unfamiliar to Earth norms. Their muscles adapt to different loads. They speak with a sense of home shaped entirely by engineered environments. Their ancestors could not have survived on Mars. They cannot imagine living on Earth. Another paradox grows from community structure. Mars forces cooperation in ways Earth does not. Small populations must maintain social stability, share responsibilities, and support one another. Yet this enforced harmony arises not from abundance, but from scarcity. Mars fosters community through necessity, not opportunity. Two opposing sentences capture it. Mars limits individual freedom. Mars expands collective resilience. The final and deepest paradox emerges when we consider the future trajectory of these settlements. Humanity moves to Mars, seeking expansion and survival, but in doing so, it builds environments where life is shaped at every level: physical, cognitive, social, and cultural. Mars becomes not a second Earth, but a second origin point, a controlled world where humanity consciously authors its future. This leads to a powerful reflection. Mars cannot support human life naturally, yet it may become the first place where human life is guided intentionally from birth onward. A last visual cue settles the subphase. Night falls. The land outside freezes in minutes. Inside, children read under soft artificial light. Plants breathe quietly in controlled greenhouses. Sensors monitor every system. Nothing outside supports them. Everything inside nurtures them, and the paradox resolves into a single calm line. Mars remains uninhabitable, yet it may become the birthplace of a new form of humanity, one shaped not by nature, but by understanding. Knowledge becomes the guiding thread that ties together every challenge of raising new generations on Mars. It replaces instinct, supplements biology, supports psychology, and shapes identity. On Earth, development unfolds within an environment that has supported life for billions of years. On Mars, development unfolds within environments humans must design, maintain, and continuously refine. This shift from natural support to engineered support forms the foundation of Martian generational life. We begin with developmental understanding, knowledge of how human bodies grow under altered gravity, radiation levels, and confined living spaces. Researchers monitor every parameter: bone density, muscle development, cardiovascular changes, sleep cycles, and nutrient absorption. Over time, patterns emerge. Which exercises help children build strength? Which diets compensate for low gravity? Which light cycles support stable circadian rhythms? This knowledge becomes cumulative, forming a medical library specific to Martian-born physiology. A visual cue grounds this. Inside a medical lab, soft blue screens show growth curves for a group of children. Some lines rise slightly higher than Earth norms, others dip lower. None are dangerous, all are data. Doctors review each trend, refining routines with calm precision. Mars does not nurture growth, but knowledge does. Next comes environmental literacy, a new form of understanding that Martian children acquire instinctively. They grow up knowing why pressure matters, why airlocks must seal, why sensors exist everywhere. They learn that cold outside is not weather but physics. They understand that oxygen comes from machines, not forests. For them, survival principles are not emergency training, they are background assumptions. A reflection fits softly. On Mars, learning about the world means learning how the world must be made. This expands into ecosystem engineering knowledge, the understanding of how closed-loop systems sustain life. Children observe how water cycles through filtration, how plants produce oxygen, how humidity affects both agriculture and machinery. They see the connections between food waste, nutrient recovery, and soil production. Mars reveals how interdependent life truly is. Two opposing sentences clarify the shift. Earth hides its cycles. Mars makes cycles visible. A microstory illustrates the clarity. A group of children visits a greenhouse on a school excursion. A botanist explains how every leaf contributes oxygen. The children watch mist rise from irrigation nozzles, see water collecting on transparent panels, and follow a pipe to a filtration tank humming quietly. Their understanding of life support is tactile, present, continuous. Now we move to psychological knowledge, essential in an environment where space is limited and isolation is the norm. Researchers study long-term group dynamics, stress patterns, family structures, and emotional resilience inside tightly controlled habitats. The lessons shape daily routines, shared meals, structured quiet hours, collaborative tasks, play periods designed to release energy in low gravity. Families learn how to maintain harmony because knowledge tells them how small fractures can compound in enclosed communities. A visual cue reflects this. In an evening gathering dome, families sit together under warm lighting. Conversations flow softly. The air feels safe. The social atmosphere is deliberately shaped, not accidental. A product of continuous research into well-being. Knowledge extends into cognitive development in artificial environments. Children raised indoors experience limited sensory variation. No wind, no natural weather, no open vistas. To support healthy cognition, habitats introduce controlled sensory stimuli. High-resolution landscape displays, variable soundscapes, and dynamic lighting mimic the complexity of Earth's environment. This is not to imitate nature exactly, but to provide the richness the brain expects for growth. A micro-thought experiment brings this to life. A child walks through a learning corridor where wall screens show forests one day, oceans the next, deserts another. The images respond to their movement, the sounds shift gently. These experiences broaden the mind while acknowledging the constraints of the planet. Another form of knowledge emerges from social continuity. The understanding that Mars communities must pass information between generations carefully. Unlike Earth, where cultures expand organically, Mars settlements rely on deliberate teaching, how to maintain systems, interpret data, respond to anomalies, and understand the environment's constant risks. Knowledge becomes heritage. A reflection fits here. On Mars, what we teach becomes the climate our children live within. Next comes identity knowledge, a subtle form of understanding that grows slowly. Martian-born individuals will have a dual identity, connected to Earth by ancestry, but shaped by a world where Earth-like conditions must be constructed. They may feel belonging inside habitats rather than outside. They may take comfort in the hum of life support machines, the way Earth-born children find comfort in wind or rain. Knowledge helps families guide this double identity, without forcing one definition of home. Two opposing sentences frame the tension. Earth gives history. Mars gives context. Now we consider evolutionary knowledge, the long-term scientific understanding of how human biology responds to new planetary environments. Mars provides controlled conditions where researchers can observe small generational shifts without rapid environmental change. Over centuries, subtle adaptations may emerge, not through uncontrolled mutation, but through informed decisions about health, exercise, nutrition, and medical care. A visual cue adds scale. In a research archive, holographic displays compare medical data across decades. Patterns form, differences appear. None indicate harm, only divergence. Humanity begins to see how biology bends when anchored to engineered environments. The final dimension of knowledge is philosophical clarity grounded in science. Living on Mars forces new questions. What defines a home? What does it mean for humans to adapt by design? How does culture evolve when nature is no longer the primary shaper of life? These questions do not drift toward abstraction. They emerge from daily interaction with a world that cannot support the simplest biological process without human intervention. A microstory offers quiet closure. A child asked why they cannot go outside without a suit. A parent explains atmospheric pressure in simple terms, showing diagrams and letting the child touch the thick glass of the window. The explanation is not fearful, it is factual. On Mars, knowledge replaces instinct as the primary guide for understanding the world, and the subphase comes to rest on a calm insight. On Mars, knowledge becomes inheritance, the structure within which new generations grow, adapt, and define what it means to live beyond Earth. Mars is uninhabitable. That truth has guided every section of this documentary, through pressure, radiation, distance, development, and the fragile mechanisms that hold life in place. And yet, the more we examine the planet's limits, the more clearly another pattern appears. Mars shows us with unusual clarity what life requires, what knowledge can replace, and how far understanding can extend when nature offers no support. A visual cue sets the final scene. Night has settled over the plains. The horizon glows faintly as residual light scatters through thin dust. The land cools instantly. Rocks radiate their heat into space. Nothing moves. The world is silent in a way Earth never is. Inside a habitat, warm light fills a corridor. Plants breathe quietly. Air circulates with steady rhythm. Humans sleep in a controlled climate that protects them from everything outside. The interior feels alive, not because Mars supports it, but because systems shaped by knowledge sustain every breath. This contrast becomes the closing insight. Mars reveals the boundary between environment and understanding, and invites us to cross it deliberately. We came to Mars because it is close enough to reach, stable enough to build upon, and predictable enough to understand. We remain interested because the planet sharpens our awareness of life's essentials: pressure, heat, water, oxygen, gravity. Elements we rarely notice on Earth become visible on Mars, outlined by their absence. The planet is not generous, it is clear. And clarity has its own kind of value. A reflection fits gently here. We learn what matters when nothing is given. Mars also forces a new perspective on time. Earth changes quickly. Weather shifts. Ecosystems rise and fall. Life reacts. On Mars, change is slow, nearly stationary. The planet keeps records rather than rewriting them. This stillness becomes a scientific advantage, a place where ancient rivers remain carved into rock, where volcanic slopes freeze mid-story, where sediments hold the memory of climates that vanished long before humanity existed. Through this lens, Mars becomes not only a destination, but a mirror. It shows Earth what it might have been without plate tectonics, without oceans, without a magnetic shield. It shows what happens when a planet cools, when its atmosphere thins, when habitability slips away. In studying Mars, we study Earth's possibilities and its fragility. The final visual cue brings the closing image. A small settlement glows against the darkness. A handful of domes, tunnels, and greenhouses placed gently on a vast, quiet world. The light they emit is human-made, steady, deliberate. It represents presence, not conquest. Survival, not colonization. Knowledge, not dominance. And the final line descends with calm clarity. Mars is uninhabitable, and yet, through understanding, it becomes a place where life persists, not because the planet allows it, but because knowledge does.